So yesterday we worked a lot with switching from exponential to log and vice versa, back and forth, because those are inverse functions. So today we're actually going to use the knowledge of inverse, exponential, and log to get the graph of the log function. Something that I know you saw a little bit last year, but you definitely didn't practice a lot. So the first question in 382 asks you for the inverse of a log. And we know the inverse operation is exponential because logs in exponentials undo each other. So the first thing I did was I'm going to switch the x and the y, the position of x and y, and then we know the inverse is an exponential. So we just have to change the form. So this is in log form. So let's change it to exponential. So the base is the little number. So that's 2. The logs are always equal to exponents. So that means x is the exponent. And then the only thing I didn't write down out of this is a y. So it's equal to y. So the inverse of my log base 2 of x is y equals 2 to the x power. These are inverse functions. All right, domain and range of our exponential. So this is old review. Exponential, I actually have it graphed. I know part C says use the table in your graphing calculator to fill it out with 2 to the x and get the graph. So if you want to go ahead and do that first, actually, why don't we do that? Let's flip-flop these. So let's use your table feature in the calculator, or you can just copy mine down. I don't care because it's going to be the same for you. And then we plot our ordered pairs. I plotted them, and this is the graph that I get for 2 to the x. That's an exponential growth because it's got a multiplier of 2. There is an asymptote. I have it written right here. There is an asymptote at y equals 0, so make sure you draw that on. I usually dot it, but I knew you wouldn't be able to see it, so I made it squiggly. And let's do the domain and range of that graph. So the domain, arrow to the left, arrow to the right. So the domain is all real numbers, which we write in interval notation, -infinity to infinity. The range, the lowest that this is going to go is 0, and that's an asymptote. So we do not hit it. So you put a parenthesis, the low is 0, the high is infinity because it goes on forever. All right, part D says reverse the x and y values in the table graph in table. So you're supposed to flip-flop the x's and y's because remember, the log function is the inverse of the exponential. So that means for inverse, all you do is flip-flop the x's and y's. So this table, this x column is going to turn into the y column. And the y column here is now the x column. So go ahead and fill that in. Just copy the y's from here into the log x's. And now we're going to plot. So I haven't done this. We're going to actually get those plotted. So 1/8 and go down 3. 1/4, go down 2. Half, down 1. 1, 0. 2, 1. 4, 2. And 8, 3. All right, so here comes my graph of the log. And we did this and we generated it by it being the inverse of the exponential. So this is my y equals log base 2 of x. So make sure you label that. And then let's get the asymptote on. So if you notice, I made my graph go closer and closer to the y-axis. That is because that's an asymptote. So go ahead and squiggle in so that you can see, and let's label it. It's x equals because it's vertical. So that's your asymptote for the log graph. So the exponential had one at y equals 0, and now the log, when we actually do the inverse, it's got it on the y-axis. All right, it says graph the line y equals x. What's the geometric relationship? So now we can dot in the line y equals x. So this has a slope of 1 because the 1's in front of the x, and it has a b value of 0. So I'm going to do this in black. So here's my 0, 0 point, and I go up 1, over 1, up 1, over 1, up 1, over 1. And then go ahead and draw that line. This is just a line that has a slope of 1. So here is my y equals x line. All right, so there's y equals x. And it asks what the geometric relationship is between the two pictures that we have. And I think most of you can see this, but it's a fold. If I pick my paper up and fold it like this on that line, it would mirror. So this green graph would land right on top of the purple. So that's called a reflection from geometry class. What is it? Reflection over the line y equals x. What's the domain and range of our log graph? So now let's do the domain and range of the purple. So domain from 0 to infinity. You don't have any negative x's. So 0 to infinity, and we have an asymptoted 0, so it's parenthesis 0 to infinity. And the range, down forever and up forever. So the range is all real numbers, which we'd write as negative infinity to positive infinity. And just to point out a real quick characteristic is when you do inverse functions, the domains and ranges flip-flop. Because the x's and y's flip-flopped, so it only makes sense that the range of the original is now the domain, and the domain of the original is now the range. All right, and then G and H just kind of review. What are the domain and range of log? When there's no base written, it's assumed as base 10. So log with no base is base 10. So we don't write base 10, we just write log for base 10. So what's the domain and range for this log graph? Well, the log graph will look the same. So it is just going to be the same as all log graphs look like that purple one, regardless of the base. They just get flatter. So it's going to have the same domain and range. We're using this purple graph, base 2. We're using that as our parent graph. All right, and then it says, what point do the graphs of log x and log base 2 of x have in common? And you can go ahead and actually graph this one. Maybe I'll throw it on here just so you see it. Let me grab a different color. Let's do it in blue. If you use your graph on your calculator, your table on your calculator for log base 10, I'm gonna do it in blue. It would have the point 1, 0, and then off the top of my head, the only other point I know is going to be this one, or I could do 1/10 and -1. All right, so here's what the graph of log base 10 looks like. It's blue. It still has the same general shape as my log base 2 graph. That's why we can go ahead and just use that as my parent. It's just flatter. So here's my log base 10 graph, the little blue one. So it's just kind of flattened out. We'll go over. It says, what points do they have in common? That's the last problem on this page. And the point, there's only one that they have in common is this guy right here. So the point 1, 0. Which is why, and I'm gonna have you note these on your paper, you need to know the locators for log graphs because we're going to be graphing them. That's what we're going to practice. So there are always going to be 2 locators I require for log graphs. The first is the point that I just said is on all log graphs. So this is locator number 1, and it is going to be the point 1, 0. All locators, or all log graphs, have this locator point. So every time I ask you to draw a log graph, you're going to start with the locator here, and then you do the transformations of wherever it's got to go. The other locator is, in this purple graph, it's 2, 1, but in my log base 10 graph, it's 10, 1. So what I want you to do is write the second locator point as base, 1. So there are 2 locators for every log graph, and it's going to be 1, 0 for everyone. And then the second locator will change depending on the base. So my purple graph had a base 2, so its locator is 2, 1. My blue graph has a base 10, so its locator is now 10, 1. If I graph log base 5, I would plot 5, 1 as my locator, and then you would do the transformations to those 2 points. So those are the 2 locators, and then every log graph has an asymptote, and it will start on the y-axis. So write that down. Every log graph will have an asymptote that starts on the y-axis. So that's the equation x equals 0. So you have an asymptote and 2 locator points. And then you do all the transformation. So if it says move the graph left 2, you take the asymptote left 2, you take the points left 2, and you draw the parent graph, the shape of the parent graph.